Welcome to review 2. So let's talk about momentum and energy. All right, so momentum is P, right? So P is equal to your mass times velocity. And so again, think back to the rhino in the toddler, where the rhino has more mass than the toddler, even though they might be going the same speed. Because of that larger mass, that rhino is going to have a larger momentum. So again, momentum is equal to your mass times velocity. And when direction isn't a factor, it can also be mass times speed. So, first question, which of the following has the least momentum? Okay, so you should have gotten an answer of B. So what you want to do is kind of work out all of the problems just so you know that you didn't mess up anywhere or you weren't just taking a guess. So on your Mcas formula sheet, you will be given this momentum equation, P is equal to mv. And so identify the mass, identify the velocity, and then multiply it out. So with that, you get B, right? 1 times 100, which is 100 kilograms meters per second, which is the units of momentum. To calculate the momentum of a pickup truck with a velocity of 25 meters per second east, it is also necessary to know which of the following. All right, so if we wanted to solve for momentum, again, which is P, and we have the velocity, then we need the mass of the pickup truck in order to do so. So the next one says, the diagrams below show a cart moving with a velocity v on a frictionless surface as a wooden block is dropped. The block then falls straight onto the moving car. Which of the following statements describes what will happen after the block lands on the moving car? Go ahead and try your best. So the answer here is C. So we can see that the cart is already moving to the right with a certain amount of velocity. And if we add more mass to the cart by adding the block, then what's going to happen is that the velocity is going to slow down a little bit. So the cart will move to the right at a velocity less than the original velocity of the car, again, due to the increase in the mass. And so it's going to affect the momentum of the cart. Okay, so let's talk about impulse and the change in momentum. So if the momentum of the object changes, either the mass or the velocity or both have changed. And so the greater the force acting on the object, the greater its change in velocity and the greater its change in momentum. And so what an impulse is a force sustained for a period of time. And so both force and time are important to changing the object's momentum. And so impulse, what it really is force times time. And we know that the force times time, or the impulse, is equal to the change in momentum. So the longer that you apply a force, the more change in momentum that's going to occur. Now, the mass doesn't necessarily change, like let's say like you're hitting a baseball, but the velocity will. And so the way that we want to think about this as well is if we need to change our momentum by, if we're driving a car and we have suddenly we have to change, whether we have to choose whether to hit a haystack or a wall, well, we want to make sure that we make the right choice, right? So if we have to change our momentum from, a velocity of like 25 meters per second to a velocity of 0 meters per second, then the haystack is the best choice. And that's because the change in momentum occurs over a longer period of time. And so with that increased time, the impact of the force is small. And so if we do choose the wall, that time is really, really short. So the change in momentum, again, to go from 25 meters per second to 0 meters per second is a shorter period of time if you choose the wall. So the impact or the force is going to be a lot larger. And so the impulse is equal to the change in momentum. So the impulse for either one of these situations is the exact same, but what you can choose is to affect the time. So if you change your momentum over a longer period of time, there's going to be a small force. If you change your momentum over a shorter period of time, there's going to be a larger force. Again, so like when you're hitting the wall, again, it's all explained here as well. So let's go to this Mcas question. So 3 students each built a device to protect an egg when it was dropped to the ground from a height of 11.5 meters. To keep the egg from breaking, each device needed to reduce the force applied to the egg to less than 25 newtons. The students dropped the device with the eggs inside and recorded some data from each device as shown in the table. So we have 3 devices, 3 masses of the eggs, 3 velocities, and 3 times to stop that egg. So which of the following tables correctly identifies whether the egg inside each device broke when the device hit the ground? All right, so the way that you need to solve this one is by using the change in momentum is equal to your impulse. So m times v is equal to your force times distance. So we're given the mass, we're given the velocity of both the egg and the velocity of the egg, but the time for the egg to stop is different. So the force of impact is going to be different. And so the shorter amount of time that it's going to take is going to, require more impact force. Okay, so what you want to do is work this out by saying, the change in momentum is equal to your impact. And by doing that, you are going to multiply your mass times velocity and divide that by the time in order to get the force or the impact. And so if you do that, you can see here on the side, the force 1 is going to be 70 newtons, force 2 is going to be 14 newtons, and force 3 is going to be 7 newtons. And so if it was less than 25 newtons, then the egg survived. So C is the right choice because device 1, that egg is going to break. Device 2, that's going to survive. Device 3, it's also going to survive. So now let's talk about the conservation of momentum. So the law of conservation of momentum states that in the absence of an external force, the momentum of the system remains unchanged. And so the important thing to remember here is Newton's third law, that for every action, there's an equal and opposite reaction. So when we're looking at the conservation of momentum, we have to focus on the system. Now the system can be more than one object, right? Usually it's more than one. And so the cannon and cannonball system. So the force that's shooting out the cannon is the exact same force that is recoiling the cannon. Sorry, let me start over. So the force that is shooting out the cannonball is the exact same magnitude of the force that is recoiling the cannon. So they're just acting in opposite directions, okay? And so the law of conservation of momentum can be applied to our cannon-cannonball system because there's an absence of an external force. So the forces are all internal to our system. So the net momentum is going to be the same as it is after, and so we can represent that with P initial is equal to P final. So the net momentum before is equal to the net momentum after. And so this gets us into the idea of collisions. So we discussed 2 different types of collisions, the elastic collision and the inelastic collision. So when the objects collide without being permanently deformed and without generating heat, that is called an elastic collision. So basically during your elastic collision, the momentum is transferred. So think of the billiard balls. So if one billiard ball was coming in with a certain amount of velocity and it was to hit the other one initially at rest, then the momentum is going to be transferred. Now remember, the mass doesn't change, but the velocity does. And so what we can do is define, the momentum of your first object plus the momentum of your second object is going to be equal to the momentum of your first object final plus the momentum of your second object final. So again, this is your elastic collision, so the mass does not change, but what is going to change is your velocity. Remember, there's going to be a transfer of momentum, and so there's going to be no heat that is generated and things do not get deformed. So a 1 kilogram block sliding to the right on a level frictionless surface with a speed of 2 meters per second collides and sticks to the second 1 kilogram block sliding to the left. After the collision, the blocks are motionless. What was the speed of the second 1 kilogram block before the collision? Okay, so if you didn't immediately recognize that it was 2 meters per second, you can use that elastic collision equation because basically they're going to transfer that momentum because your final momentum is equal to 0 because they're motionless afterwards. And so when something is at rest, it has no momentum. So what we can do is we can set the momentum of the first block plus the momentum of the second block equal to your final momentum of 0, because again, they're at rest at the end. And so if you do that, then your mass is the same for both, 1 kilogram, and the velocity of V1 is 2 meters per second. Then you can work out some math. I've designated the left side as the negative side, the right side as the positive side. So you should get a V2 is equal to -2, or 2 meters per second in the opposite direction. So our next type of collision is the inelastic collision equation, and this is the one where your objects are going to stick together or they're going to deform, and there's also going to be heat that is generated. And so the equation for your inelastic collision can look one of two ways. If your objects are initially starting together and then they separate out, then it's going to look like the first one. So the mass starts combined and then they separate. So like, let's say that somebody was like, I don't know, throwing a tool or something like that. So they initially had it in their hand, and then that collision point would be when they are releasing that tool. And so your two objects are going to have two different velocities at the end. If your objects are starting out separately and then coming together, then and they stick together, then their masses are going to combine and they're going to end with a certain amount of final velocity together. So the mass combines, ends with the same final velocity, heat is generated, and there's a deforming that happens because those objects are sticking together. So a good example of that is like with your freight cars, or maybe like the big fish eating the smaller fish. Again, those masses are combining and they're both moving with the same amount of final velocity at the end. So two carts with different masses are both moving to the right. The mass and initial velocity of each cart are shown in the diagram. So V1 has 2 meters per second of velocity, and then they're different masses, and then V2, 1 meter per second, and then M2 is 0.5 kilograms. So the carts collide and then stick together as shown below. What is the speed and direction of the carts after the collision? All right, so if you use your inelastic collision equation, m1v1 plus m2v2 is equal to the masses combined times the final velocity, you should get a final velocity of 1.7 meters per second to the right. So let's kind of go over it. So you would start by finding your initial total momentum. Adding both the momentum of the first cart to the momentum of the second cart and setting that equal to your final momentum. So again, the carts are combined and they're going to move away with one type of final velocity. And then you just kind of do the math with that. And so once you do the math, you're going to get the momentum of the first cart is 2.4 kilogram meters per second, and the second one 0.5 kilogram meters per second. Then you're going to add those together, and so your total momentum initial is equal to 2.9 kilogram meters per second. Now your initial momentum has to equal your final momentum, again, just due to the conservation of momentum. And so if you add those two masses of the carts together, 1.7 kilograms, what you're going to do is divide that by your initial momentum, and that's going to give you your final velocity of that cart in order to have the conservation of momentum, in order for both the momentums of your initial and final to be equal. And then the direction has to be to the right, again, because there is the velocity going to the right is more than what's acting to the left. There's actually nothing acting to the left. Okay, so let's talk about energy, work, and power. So energy is like the ability to do something. Think about in terms of like the ability to do damage. And what we're mainly concerned with is mechanical energy, and what that consists of is potential energy and kinetic energy. So potential energy is an object that can store energy due to its position. So what that means is if like I was to lift the bowling ball like an inch above your head, or like 12 feet above your head, again, that bowling ball has more potential energy or more stored energy, and so it has more potential to do damage. Or to think about the bow being drawn back on a bow and arrow, again, more potential to do damage. And so sometimes changing the position of your object makes it more dangerous, right? We just kind of saw a couple of examples of that. So again, think of your pendulum. And so if you were to increase the object or like the mass of that object up in the air, again, you've increased the potential energy of that object. And that's because we're mostly talking about gravitational potential energy. And so energy is stored by an object due to its vertical position or height. So this is also due to the gravitational attraction of the Earth or the acceleration due to gravity. And so if you let the object go, that force will act on the object and move it faster and faster towards the Earth. So when we're talking about potential energy or gravitational potential energy, we use the equation PE is equal to mgh, where m is the mass of your object in kilograms, g is the acceleration due to gravity, 10 meters per second squared, and h is the height of the object, or in meters, okay? So all energy is measured in joules, so potential energy is also measured in joules. So a 2-kilogram cart is released from the top of the ramp that is 1 meter high. 3 positions of the cart are shown in the diagram. Assume friction is negligible, so ignore friction. Which of the following tables correctly shows the cart's gravitational potential energy and kinetic energy at positions A, B, and C? So remember back to the conservation of energy and how energy is transferred, and do your best answering this question. Okay, so let's go over this. So what you want to do is first solve for the potential energy at the highest height, because at the highest point, the potential energy is going to be the highest, because remember, potential energy depends on mass, G and H. G is a constant, H is the height, and N is the mass of the object. And so we're told that the mass of the object is 2 kilograms. From the chart, we know that the height is 1 meter. We know G is a constant of 10 meters per second squared. So the potential energy at point A is 20 joules. And so we then can kind of cancel out a couple of things. We can cancel out B, and we can cancel out C, okay? Because we know at point A, the highest potential energy is 20 joules. Okay, and so from there, we know just from the ideas of the conservation of energy, which means that energy can neither be created nor destroyed, that this energy, potential energy, is going to transfer into kinetic energy. And so at the lowest point, at C, it's going to have the highest kinetic energy. And so D and A, again, are only things left. All right, so then we have to look at our choices for B. And so our choices for B at A is 15 and 5. And now if we add the gravitational potential energy of 15 joules plus 5 joules, we're going to get the total energy. We're going to get 20 joules. But if we add together gravitational potential energy of 15 joules and 10 joules, we're going to get 25 joules. And so again, we can't create nor destroy energy. And so A is your best choice because B has added some energy in there. And so that cannot happen. So A has to be the best choice there. All right, so let's talk about kinetic energy. Kinetic energy is the energy of motion in any direction. And kinetic energy is equal to 1/2 mv squared, where m is the mass of the object in kilograms, v is the velocity of the object in meters per second. And again, kinetic energy is an energy, so we measure it in joules. And now kinetic energy is technically a scalar quantity because it doesn't depend on direction, it only depends on magnitude. So as the mass increases, your kinetic energy also increases proportionally. As your speed increases, the kinetic energy increases as the square of the speed. And again, look back on that equation so that you can verify that. So a student releases 2 objects at rest, W and X, from the same height above the ground. The table shows the masses of the objects and the height from which the student dropped them. So we have object W and X, we have the mass in kilograms, and we have the height. Which of the following describes W's kinetic energy just before both objects hit the ground? All right, so from the conservation of energy, energy can neither be created nor destroyed. And so because we're given the mass and the height, what we want to do is we want to solve for the potential energy for W and for X. And so we have the mass of 7 kilograms, the height of 4 meters for W, and so we can multiply that by G, our constant, and we'll get 280 joules. And so what we know is like all of that potential energy is going to transfer into kinetic energy once that object is dropped. And so the energy just before it hits the ground is going to be 280 joules. And so if we look at X and we do the exact same thing but with different masses and different heights, we're going to get a potential energy of 200 joules. And again, just before the object hits the ground, the potential energy is going to transfer all the way into kinetic energy. And so we're going to be 200 joules of kinetic energy. So what that tells us is that C, object W's kinetic energy was greater than object K's kinetic energy. So remember back that mechanical energy is made up of both potential and kinetic energy, and they often act together or at the same time. And so if that object is in motion and going up a hill, that kinetic energy is going to be transferring into potential energy at the highest point. It's going to have the highest potential energy, again, because potential energy depends on mass g and height. And then as that object goes down the hill, the potential energy is going to transfer into kinetic energy. And again, this stems from the idea of the conservation of energy. Energy cannot be created nor destroyed. And so what that means is that your mechanical energy initial is equal to your mechanical energy final. So the potential energy plus kinetic energy initial is equal to the potential energy plus kinetic energy final. So what that means is energy is conserved. So again, when you're looking at your pendulum at the highest height of that object, you're going to have the highest potential energy, and your kinetic energy is going to be 0. And at that midline, as it's going the fastest, your kinetic energy is going to be at the max and your potential energy is going to be 0. And so you're going to have a constant swinging back and forth. And so your total energy is always going to remain the same, but your potential and kinetic energy are going to be transferring in between. A student rides a bicycle down a hill and then up another hill without pedaling. Which of the following statements best describes what happens to the energy of the student and the bicycle while they move up the hill? So when the bicycle and the student are moving up the hill, they are increasing their height. So there's going to be an increase in your potential energy. Now remember, you cannot create nor destroy energy, so this has to be coming from the kinetic energy. And so the kinetic energy is going to be transferring into potential energy. So your kinetic energy is going to be lost and your potential energy is going to be gained. But remember, the sum of those things does not change. An engineer is constructing a device that turns electrical energy into mechanical energy. The engineer notices that some of the electrical energy also turns into thermal energy. Which of the following describes how the device can reach maximum efficiency? So when we're looking at the ideas of efficiency, we want to maximize the potential and kinetic energy. And so what that means is we want to minimize the energy that is lost due to heat or thermal energy. And so we want our device to minimize thermal energy, but maximize this potential and kinetic energy so that we can get the most motion or the most stored energy out of the device. All right, so C is the best answer choice for this, again, because we want to minimize that heat loss. Okay, again, that's just like the loss of energy due to heat. And so we want to maintain that energy so that we can use it for our device. All right, so let's talk about work. So work, a force acting upon an object causes a displacement. So what that means is if you have a force times a distance, then you're going to be doing work. Now, work is measured in joules, but what's important about work is the force has to be in the direction of motion. If the force is not in the direction of motion, then no work is done. And so an example of this would be like lifting up a suitcase while moving to the right. Well, if that direction of motion is to the right, but the force is acting up, then there's going to be no work done on that object. If you're moving to the right and the force is being applied to the right, then work is being done on that object. So neglecting friction, which of the following statements describes the relationship between the energy of an object and the work done on it? All right, so let's look at these answer choices. Work is needed for an object to keep at a constant kinetic energy. Not necessarily true, so let's just cancel that one out. Work is needed for an object to keep at a constant potential energy. Nah. Increasing the potential energy of an object decreases the amount of work needed to stop it. That would be the opposite. An increase in potential energy, there would be an increase in work needed to stop it. And so the increasing in the kinetic energy of an object increases the amount of work needed to stop it. That is the only one that is true. And so if you look back at our equation, kinetic energy is equal to 1/2 mv squared. The more velocity that you have, the more momentum that you have. And the more momentum that you have, the more force that is needed to stop that momentum. And so that force is equal to your distance over time. So really, that's work. All right, so the more work that is required in order to stop it. So power is the rate of doing work. And so power is work over time, and we measure power in watts.